So good morning, everyone. Let's start today's session. In previous session, we learned about the photoelectric effect, the effect where the photons generate electrons. When a photon having sufficient energy is struck on is fallen on a metal, and it could emit electrons from that. So that phenomena we discussed. So they are right. But previously in third module, the matter radiation. So the third module, the waves and oscillation module, we learned the light is a electromagnetic wave. Right. So uh, light is electromagnetic wave which displays some properties related to waves like diffraction, reflection, refraction, and interference. So those kind of properties we discussed. But here the photoelectric effect, right? So it is somewhat, it cannot be described using the way, only using the properties or using how we treated the waves in that module. Right. So if we consider just electromagnetic, for example, light is a ray, it's a wave, then we cannot express this photoelectric effect phenomena, right? So can you understand that? So when we consider the behavior of light as a wave, this phenomena called the photoelectric effect cannot be described, right? Because they are what happens, we introduced something called photon. So that photoelectric effect is addressed or is studied, discussed using another theory called the quantum effect, right? Quantum, or we call it a photon, right? Photon. So we consider any wave consists of millions of photons, more like small particles. So when a photon, like kind of that particle, hits on a metal having sufficient amount of energy, that metal absorb heat and release heat. Metal absorb energy and release electrons out, right? Release electrons out. And that's how it could be described, not using the properties of waves, right? And there's another effect called the quantum effect. It's the scattering of photon by electron to any other charged particle. Scattering means the uh, change in path of a photon by another charged particle, so which is discovered by Arthur Compton. So this phenomena also could not be explained using the basic properties of wave, basic behavior of waves. So to describe these properties, Einstein and some other scientists came up with this concept called uh, photon, right? Photon, a quantum, right? So using that method, all these photoelectric quantum effect could be described. Right? So now we understand that light or electromagnetic wave would behave sometimes. Sometimes it behaves according to wave, it shows wave properties, and sometimes it shows particle properties of behaves according to particle, right? So uh, that incident, right? So later, the scientist Louis de Broglie in 1924, a French scientist, he made an argument. Not only the light could behave either. Uh, not only light could behave sometimes as a wave, sometimes it could behave as a particle. He said that all the matters, right? Any object, like your tennis ball or your phone, anything, right? Anything could, they could show all these two variation. So a uh, simple tennis ball also could show some maybe small amount of behavior according to relevant to waves. So likewise, so all these objects, any objects could behave according to sometimes according to a wave, sometimes according to particle, right? So that, but uh, all the object, right? That biasing is different, right? So normally, if we consider light, it shows more property related to wave, not to particles. But when it comes to a ball, it shows more properties related to particles, not waves. So when we consider uh, ball, it is more biased towards the towards a particle, towards the nature of particle. But when it comes to visible light, it is more biased towards the behavior of waves. But that doesn't mean it is completely uh, it is, although it is somewhat biased towards the properties of wave, it could sometimes show the properties of particles, as we discussed in photoelectric effect. And so that concept was introduced by Louis de Broglie in 1924, and he was able to come up with the formulation as well. So let's look at that one. And so in 1924, French scientist Louis de Broglie in 1924, French scientist Louis de Broglie uh, argued and made an argument in 1920, French scientist Louis de Broglie made an argument that uh, any object uh, or wave would show both properties related to both properties related to waves and particles. Yes. Particles. So any object could show both properties related to waves and particles. But uh, they are the composition of the properties would be vary. For some object could be biased more towards the properties, towards the nature of particles, some towards the nature of waves. But some are biased towards uh, some are biased towards particles. The nature of particles, and some are towards waves. Right? Then from the Einstein's equation, for the relation between uh, mass energy conversion equal mc square. I can write E over C is equal mc. Right here, c is the velocity of light, m is the mass of the particle. Velocity of light 10 to the power 8. M is the mass of particle. Particle is the energy. Mass of yes, mass of particle. Mass of particle is the corresponding energy. The particle. And so mc is the m into a. Mass into velocity is the momentum. The particle. So p is equal EOC. P equal EOC. Right. So then from Planck's equation is equal HF or HC over lambda. And combining this first and second equation, so you see first and second equation, P is equal HC over lambda into C. So C get cancelled out. We have lambda is equal H over P. H over P. Let's here lambda is called the de Broglie wavelength. H is Planck constant. P is the momentum of the particle. P is the momentum of the particle. So this shows the wave. This is called this behavior of both wave and this behavior of both uh, wave and particle nature of matters is called as wave uh, particle duality. This is referred as wave particle duality. Right? Wave particle duality. Now let's, for example, try to find the wave particle duality for ball and electron. Right? Ball and electron. Right? So consider a ball get velocity velocity 20 to ms minus 1 and having a mass of 0.14 kilogram and consider an electron moving at velocity that consider electron moving at velocity 5.8 10 to the power 6 and 9.11 10 to the power minus 31. Point to 10 to the power 6 minus 1 and having and having a mass of 9.11 10 to the minus 31. Right. So the question is find de Broglie's wavelength. Right. Find de Broglie's wavelength. For ball, lambda is equal so here we have HC over MV, where H is 6.6 10 to the power minus 34. The value of Planck constant is 6.6 10 to the power minus 34 divided by M is 0.1.222. Right, so answer we get 3.08. No, no, 2.15 10 to the power minus 34. To the power minus 34 meters. For the electron, right? For the electron, so H over MB 6.6 into the power minus 34 is the Planck constant divided by mass is 9.11 1 to the power minus 31 into 5.8 to the power 6. 10 to the power 6, 0.12 nanometers. 0.12 into 10 to the power minus 9, minus 9 is nanometers. Nanometers. So here we can see clearly that we already know from our intuition that electron is more biased towards the nature of a wave than a ball. And ball, we from our childhood we consider ball as a particle, right? It doesn't, we don't consider it as a wave. So here we can see the wavelength, the de Broglie wavelength corresponding to ball is 2.15 to the minus 30, which is very small. Which is very small. For electron, the wavelength is considerably higher, right? Considerably higher compared to the ball. So which means the electron is showing more nature of wave than a ball. Right? So here the obtained de Broglie's wavelength here the obtained de Broglie's wavelength of 10 de Broglie's wavelength of the obtained de Broglie's wavelength of wavelength of electron is much higher compared to the ball. To the ball. Hence, it is clear that uh, the electron hence it is clear that electrons show more nature, right? More behavior of waves of waves than a ball, as simple ball, right? So it is. I think now it is clear. Right? So this relation is called wave particle duality. Right? Wave particle duality. This lambda is the de Broglie's wavelength. Wave particle duality. So here we got a very small value for volt, the wavelength, which means it shows very least amount of properties related to waves. But for electron, we get some sufficient higher value for the wavelength, which implies that shows more behavior, more nature, comply with waves. Right? Here, this is another experiment done on electrons. The two scientists, C.J. Davison and L.H. Gardner, first time. So it was verified. So this is just a concept, latest concept. Then this Broglie theorem was verified by this Ultra and this L.H. Gardner and C.J. Davison. Has a wave nature. The electrons has wave nature as well. So the experiment is here the electron beam is subjected to towards that electron wave is subjected towards a metal a crystal electron crystal, and after the diffraction process, what is diffraction? We learned that property of diffraction is the variation, is the deviation of the wave's path from its uh, original from its original one due to encounter due to the edges, uh, due to the edges and other blockages. Right? So when the waves hit on edge like this, it would get deviated. Path would be deviated. Thomson. Right? So here also it could be shown that observe that after the diffraction through the crystal, the variation of the intensity of electron beam shows this pattern is somewhat similar to X-rays, right? So X-ray is a wave, X-ray is a wave. X-ray is considered as a wave. So when X-rays fallen on a crystal as well, it would show the same pattern as the beam of electrons. So So it could be verified that the electrons also shows wave nature. Right, so the X-ray diffraction, here the X-ray diffraction, so earlier there was a big issue of having diffraction, observing diffraction of X-rays, because X-rays have wavelength of nanometers, right? Very small wavelength, right? Very small wavelength compared to the electron. So electrons has not electrons, the light, visible light has visible light it has a wavelength of 400 nanometers to 700 nanometers, whereas X-ray has around 1 nanometer of wavelength, which is very small. Right, so here to observe the diffraction, so normally, so there should be there's a gap, right? There is a gap, and the wavelength of the wave, right? So if the wavelength is less than that of gap, it would get diffracted. But if the gap is very larger, like this, then the wave, it won't be diffracted, right? Won't be diffracted to just go through the gap, because the gap is sufficient to move through without any diffraction, right? Here, so you can see X-ray is having very small wavelength, so gap also should be very small to observe the this diffraction property, diffraction nature of electrons, oh sorry, extrons. X-rays, gap should be very small, right? If the wavelength is very small, the gap also should be very small in order to observe the diffraction. So earlier the scientists could produce artificial materials to find the diffraction of visible light. It was okay, right? So 400 nanometers, 700 nanometers, they could do that. They could do that, uh, artificially formulate very small gratings comply with the visible light, but not X-rays. At X-rays, they could not build very small spaces or gaps of 1 nanometers. Right? It was almost impossible. But later, this scientist, Maxwell law, so he found that there are crystals having uh, small spaces in between the crystal particles that is that comply with this that complies or that comply with the diffraction of X-rays that could show or that could be used to observe the diffraction of X-rays. So which means the gap between, so here if we consider sodium chloride lattice, the gap between two atoms almost equal to 1 nanometer, and almost equal to 1 nanometer. So they could be used, right? So naturally, they could be used. Naturally, they could be used. So he was able to find that, and with the experiment like this, there are natural materials which could diffract X-rays. That was his finding. Right. So using this same concept of the wave nature of electrons, this electron microscope is constructed, electron microscope. So normally, in order to observe something, the wave should hit on the object and reflect and come to a wire. And that's how the normal process happens. So for the first wave should propagate or directed hits on the object and reflect again and comes back towards the wire. But if it is not reflected, means if the wavelength is very small, if the particle is small, right? If the wavelength is larger enough than the object, it could get reflected. Okay, it's okay. But if the object is very small than the wavelength, then it would not get reflected. And it would get reflected. So it would not reflect if the wavelength is higher than very high. Wavelength is larger than the object which is being observed. It would not be reflected. So it cannot be seen. It cannot be seen. Cannot be seen. Right. So visible light only. So we know the visible light is having both of 400 meters or 700 meters. So very small particles, like in nanometer ranges, like photons, very small particles could not be observed using this typical microscope, optical microscope, which is shown on the right side here, left side figure, because the wavelength is higher than the object, right? Higher than the object, so it won't be reflected by the object, right? So the people could, so this is a typical light, the optical microscope. So people build the electron microscope. So if the electrons are accelerated to a very high velocity, their wavelengths become very small according to this de Broglie's relation. Right? When so this again I can write is equal h over mv, right? So when v is very small, lambda is very low, right? When v is very high, lambda is very low. So by accelerating electrons into very high into a very high velocity, it could be the wavelength could be brought down. So that is the thing implemented on the electron microscope. First, it is accelerated to very high velocity, and then electrons are shooted and diffracted. Right, the path is changed using this lens, electromagnetic lens. Here we use the typical optical lens in optical micros. Here, electromagnetic lasers. They are called electromagnetic lasers because the path of the electrons could be deviated using electromagnetic lens by changing the strength of the electromagnetic waves around that. Right? So same concept, only difference is here electron highly accelerated electrons are used, and the lenses are not glass, the optical lenses, they are electromagnetic lenses. Right, so now let's consider and consider some electrons. Right, so and if an electron if an electron is if an electron is accelerated if an electron is accelerated if an electron is accelerated to high velocity using voltage difference like this using an electric field actually. Right, so this is the electron initial velocities let's say V0, and after reaching the other side let's say it is V. So potential difference is V, capital V. So by conservation of energy, you can write, right? By conservation of energy I can write EV, capital V is equal half mv squared. The uh, potential, the work done by the electric field is equal to the kinetic energy stored in the electron, half mv square. Right, 2 uh, m capital V is equal mv over squared. So P is equal to EMV. Right, 2 EMV. P is equal to EMV. Right, so by plugging this to the typical equation for the Broglie's, we have another equation, lambda is equal to H over from the Broglie's wavelength. Right, so lambda is equal H over 2 EMV square. Right, so V is the potential difference. Capital potential difference. Now let's consider that if an electron of m mass of electron is 9.1 and the power minus 31. E is charge 1.6 10 to the power 19. 1.6 in 10 to the power 19 coulomb. 19 coulomb. So Planck constant is 6.6 10 to the power minus 34. Joules S. And if E is accelerated across a potential difference 3600. 3600. The lambda you would get 6 in 10 to the power minus 11. That's a by you can apply for this equation. Lambda is equal 10 to the power minus 34. Two into 1.6 10 to the power 19. M is 9.1 10 to the power 31. B is so lambda is 2 in 10 to the power minus 11. Minus 11 meters. A very small wavelength, right? So the resolving power is wavelength of accelerated electron is higher than the uh, wavelength of light. Threshold power of electron microscope is electron microscope. Threshold power of electron microscope is very higher than optical microscope. Yeah. Then this is just a comparison of the electron microscope, of electron microscope and optical microscope. The obtainable magnification is, so you can see that electron microscope is higher than 100,000, whereas it is in the 1,000 and 15,000 for optical microscope. Maximum resolution is also very less, around 0.5 nanometers. Here source is visible light of optical microscope. There beam of light, beam of electron for electron microscope. Inside the microscope it is just air. The optical one, electron, it is vacuum. Lens type glass and electromagnetic. Because of contrast, differential absorption of light, irradiation of electron, focusing process, focusing in the lens, changing the current to the electromagnet. And by changing the current to the electromagnet, the electromagnetic, the strength of the electromagnet wave will be changed. So accordingly, the focusing process happens. Right now, let's move on to the X-ray generation process. So before that, let's just look at this cathode ray. What are cathode ray? Which were discovered earlier than the X-rays. So it's a cathode tube consist of anode and cathode and glass tube. So the scientist William Crookes found that when it is subjected to very high voltage, some B, right? So this is not the backbone. Inside this tube is there are some kind of gas incorporated into the glass tube, and when it is subject to very high potential, the beam, colorful beam, is propagated towards the cathode anode. But earlier, uh, the William Crookes could not identify what it is. But after, so it was around 1870. So after J.J. Thomson found the electron in 1879, right, so they were able to describe this phenomena. Right? So earlier they just observed some beam is emitted from the cathode and travels towards the anode, like using the experiments, and later they determined and they uh, gave this one, and they could describe those are electrons, and those are electrons. And from the experiment done by the J.J. Thomson, he found that uh, cathode rays have been found. Right? So earlier it was called as cathode ray. Actually, they are the electrons. The beam of electrons are the cathode rays. That's cathode rays. Beam of electron. Right. So these always emitted from the cathode and directed towards the anode. And these are emitted from cathode and directed towards the anode. And they show rectilinear motion. This ray, they show rectilinear motion. They show rectilinear motion. And no matter the type of air inside the tube, they show same property. Matter the type of air inside the tube, the rays show same energy. those same properties. But they have same properties and they have kinetic energy as well. And they can be deviated from both electric and magnetic field. Can be deviated from both. Their path can be deviated from both uh, electric and so these properties are found in the cathode rays. They are the beam of electrons. And the most important observation is when these electrons hit on other, uh, when these electrons are fallen, or when these electrons hit on other matters, X-rays are emitted. When these rays are hit on other other uh, gases or other matters, hit on other matters, other matters, X-rays are emitted. But X-rays are emitted, so which was a fascinating discovery. Right. So first, in 1895, this German physicist Wilhelm Röntgen made the groundbreaking uh, discovery of these X-rays when he was doing an experiment as before. So he discovered that uh, when a when a cathode tube like this charge tube is filled with low pressure air and pumped into high voltage, some fluorescent screen coated with barium platinoxide began to glow. Right? So even though it was not directed contact with the tube, additionally he observed that photographic film tightly wrapped in black paper became formed when placed near the discharge tube. Right. So he discovered some invisible rays was being emitted from the tube. Right. He observed some invisible rays entered from the tube and we named this as X-ray and X-rays. So basically the generation of X-rays can be basic apparatus for generation X-ray is as follows. So the basic for generation, basic setup for generation of X rays are as follows. The basic setup for generation of X-rays are as follows. So there is a anode and a so this is cathode and anode. It's called as target anode. This is a vacuum. So this anode and cathode is subjected to very high potential. Right, so this is called the target anode. This cathode, right? Target anode, cathode. Uh, so this is the first circuit. So this is a very high voltage. Around 10 to the power 10 to the power 5 volt. 10 to the power 5 volt. And there is another circuit just to generate the electron. So here the using this filament, uh, using this filament, the electrons are generated. So it's a little low voltage. And so just a filament. Here it is vacuum. Here it is very low voltage. around 10 volt. So this is a filament. So here the process is from the filament bulb. By applying low voltage filament, electrons are generated here, and these electrons are accelerated towards the target anode, which is made from tungsten or molybdenum. Uh, and when the electrons hit on the target anode, the X-rays are X-rays are generated. So that's how it goes. X-rays are generated from the target anode. So first the electrons are uh, generated from the filament bulb. Here, first the electrons are generated from here first the electrons are generated from the heated filament. from the heated here first the electrons are generated from the heated filament using the low voltage source. Right, using the low voltage source. Uh, then the emitted electrons, the emitted electrons from the cathode is accelerated towards the anode. Cathode accelerate towards the anode using high potential difference. Those electrons hit on the target anode. Generate X-rays. Generate X-rays. So this is some kind of a reverse process of photoelectric. In photoelectric effect, first the photons generate. Photon types of generate electrons. Here the electron generate X-rays of photons, right? So this can be addressed as the reverse process of photoelectric effect as well. So this could be identified as the reverse process of photoelectric effect. The reverse process of photoelectric effect. That's all. If the applied potential difference is V, is V, and frequency of generated X-rays I X-rays IF. If no energy is lost, no energy are lost. If no energy is lost, if no energy is lost, EV, total energy gained by the potential difference, is converted to HF max. That EV is HF max, or it is half mv square. HF max, or HC over lambda min, right? Lambda min. So lambda is here when frequency is highest. So this is how it goes. So here the tube is vacuumed to have minimum obstruction to the flow of electron. Minimum obstruction to the flow of electrons. And the target anode is, since the X-rays are emitted from the target anode is made of very high boiling point and molar mass. Made of high molar mass, and the target anode is made of high molar mass and and high boiling point. High boiling point. Yes, high molar mass and high boiling point. Right, so that's how it goes. The generation of X-ray. Basically, the electrons are generated from low voltage and directed towards the target anode, and when plus highly accelerated electrons hit on the target anode, X-rays are generated. At here, the some important fact: only one electron could generate one photon. So combination of electrons could generate a photon. Only one electron could generate one X-ray. X-ray photon. So combination of electrons could generate one X-ray photon. Right. So by controlling the X-ray beams, these photos, the X-ray photo can be obtained as here, as shown here. And so the X-rays having high intensity, high energy could penetrate to the skin, but not to the bones. So when there's an X-ray photographic film on the other side, so this region which are exposed to X-rays are covered black, and the other regions which are not exposed to X-rays are white. So that's how the X-ray image is formed. So here you can see the bones are shown as white and the other region black. So there are many advantages of these X-rays, which are described here. X-ray electromagnetic waves and wave short length and frequency. They are not deflected by electromagnetic field. And they don't have a charge. They are not deflected by electromagnetic field. Charge particles. This can penetrate into matter, can be almost totally plate of lead, thickness of 1 millimeter. And to get protected from X-rays, covers may be plates of lead are used. It can be focused by lens when traveling through different media. They can deviate very little for something required to know the more nearly equal to crystallatics. They can refract by crystallatics. Are sensitive to X-rays. X-rays make photoelectric emission. So X-ray could be used to make photoelectric emission, and that we discussed before. So some other applications, usages of X-rays to identify the outer space. To study the outer space, X-rays are used. Imagine engineering to find the faults in internal metal structure, joints, rails, and rivets. Right. So that's all about this X-ray, wave particle duality part, and X-rays generation. So let's go for that. Some question first. So let's try this question. The third question first. Third question. When a free particle with kinetic energy K and de Broglie wavelength lambda enters a certain region, its potential energy becomes weak. The particle's new de Broglie wavelength is given by when a free particle with kinetic energy K and de Broglie wavelength lambda enters a certain region. Free particle with kinetic energy K and de Broglie lambda enters its potential energy becomes weak. Particle new de Broglie wavelength is given by. And so total energy is equal to the potential energy plus the kinetic energy. So how to go for this one? So we have lambda is equal H that lambda is equal H MV or P at MV or P and so then we were able to show that P is equal square root to MEB, potential difference, kinetic energy. Right, so then half mv squared is the kinetic energy. 2 into m k is p squared. So p is equal square root 2m k. So I can rewrite this de Broglie equation in terms of kinetic energy. Lambda is equal h over 2mk square. At lambda over 2mk. Here lambda is not lambda. Yes, yeah, k is the potential energy. So I can write lambda is proportional to 1 over k square root. All the others are constant. Right, so for the two instances, lambda dash would be proportional to 1 over, so potential energy when the total energy is constant. So the potential energy would be so the potential energy increases to V. So the total kinetic energy would be K minus V. So total energy is K initially. In the first case, first E total is just potential energy, first case. And after entering to second layer, second case, E total is K dash plus V. So K dash is, so it is K minus V, K dash. So second kinetic energy is K dash, which is K minus V. Then by lambda over lambda dash with the other is K minus V dash is lambda like this. Answer is Yeah, this should be K. Should be K. Second one is the answer. Mistake. Second question, an electron of mass mv when accelerated through a potential difference has the Broglie wavelength of lambda. The Broglie wavelength associated with a proton of mass mp accelerated through the same potential difference would be. So lambda is h over 2 e mv potential difference. So if all the others can remain same, we have lambda is proportional to 1 over v. So m potential difference is kept constant, and is kept constant charge. We have mass. So lambda is proportional to n. Lambda dash is 1 over mp. So 1 divided by 2 is divided by 2 divided by 1 dash lambda. mv over mp. Lambda mv over mp. Right, mp, right? Should be mp, not mv. mp. The second answer. And which of the following statements made about X-rays is not true? Not true. In vacuum, X-rays propagate with the speed of light. Correct. X-ray can be refracted to crystal lattice. Yes. X-rays can produce photoelectric. Yes. X-ray can be deflected by electric magnetic field. Can analyze gas. Not true. Photons cannot be reflected using electromagnetic field. Right, a photon fired at the atomic nucleus, which is positive charge. Photon is also positive. Photon is also positive charged. Diagonal not possible, so it cannot be attracted towards the nucleus. So it can be deviated away from the nucleus, not attracted. Which of the following statement regarding the X-ray production in common application is incorrect? Regarding X-ray production, common application is incorrect. Two circuits have been used, yes. And it could be damaged due to bombardment, yes. The voltage sufficient to heat the cathode, yes. Energy of X-ray emitted depends on the current from the filament. X-rays tube must be able to avoid the loss of electrons. Yes. No, energy of X-rays emitted depends on the current through the film. That's incorrect. That's the energy of X-ray emitted depends on the current through the film. That's incorrect. That depends on the voltage difference. Depends on high voltage. The voltage has been applied across. Uh, depends on voltage. Voltage, which is being applied across the anode and cathode. Anode and cathode. So in this session, we basically talk about wave particle duality, Broglie's equation, and basically entropy, and the formation of X-rays, and like uh, how the electron microscope work. So this is just the inverse of the reverse process of photoelectric effect, the formation of X-rays. So in next session, we will move on to the radioactivity part. Uh, how what are gamma rays? We will study about gamma rays, alpha rays, and beta rays, and nuclear reactions, and move on to the module. So, thank you.